Hello everyone and welcome to Pepcoding. I hope you all are extremely good. So today in this video we are going to discuss another question on graph, that is to remove the maximum number of edges to keep the graph fully traversable, right? So in this graph, what we are given in this question, that Alice and Bob have an undirected graph of n nodes and three type of edges, right? So we are given a graph that is undirected, right? And we are given three type of edges, right? Type 1 can be traversed by Alice only, type 2 can be traversed by Bob only, type 3 can be traversed by both of them, right? So given we are given with an array of edges where the first column is representing the type of the edge, and this second column is representing the source of the edge, and the third column is representing the destination, right? So we are given this array of edges, and we have to find out that how many maximum number of edges we can remove from this graph, such that after the removal of that edges the graph is fully traversable for both the Alice and Bob, right? So what does this mean? That the graph should remain connected for Alice and Bob even after the removal of that much number of edges, right? So also it is given that return the maximum number of edges you can remove, or return -1 if it is impossible for the graph to be fully traversed by Alice and Bob. That is, it is possible that the graph is not fully traversable by Alice and Bob with the given edges. So in that case we have to return -1, right? So for example, we are given this array of edges, right? So this column is representing the type of edges, right? So type 1 is representing that this edge can be traversed by Alice only. Type 2 is representing that this edge can be traversed by Bob only. Type 3 is representing that this edge can be traversed by both the Alice and as well as Bob, right? So this is representing the type of the edge, and this is representing the source and the destination of the edge, right? So let's draw this graph. So there are four vertices, 1, 2, 3 and 4, right? So the first, let's represent the type number 3 edge with blue color. Type 3. This can be traversed by both Alice and Bob, right? Let's represent type 1 edge with red color by Alice only. Type 3 edge with green color can be traversed by Bob only. Type 2, right? So the first edge we are given with is 1, 2. This is of type 1, right? So this is an edge. Next again 1, 2, but this is of type 1, right? So type 1 is of red color, so this is also an edge, right? Next is 1, 3. This is of type 1, right? Next is 2, 4. This is also of type 1. Next is 2, 3. This is of type 3. Next is 3, 4. This is of type 2, right? So the only Alice can go from 1 to 2 by using this edge. Only Bob can go from 3 to 4 by using this edge, right? So we have to remove the edges, remove the maximum number of edges, so that after the removal the graph is fully traversable by both Alice and Bob, right? So how can we do this? So we can create a DSU for both Alice and Bob, right? So let's create DSU for Alice. Let's name this as parent of Alice, and a DSU for Bob. So DSU for Bob. Let's name this as parent of B, right? So initially there are 4 vertices. Bob also have to travel all the vertices, right? So 4 vertices. Also we have to keep the track of the vertices visited by Bob and Alice, right? So let's count A is representing the vertices visited by Alice and count B is representing the vertices visited by Bob, right? So initially these are 0, right? Next we also have to keep a count of the number of edges we can remove, right? So let's take another variable, that is remove edges. So initially it is also 0. We will increment this variable if we find a edge that can be removed, and after the removal of that edge we are able Alice and Bob are able to traverse the graph fully, right? So firstly, now here you can see that the preference of type 3 edge is always more than 1 and 2. Why? Because by using this edge, both Alice and Bob can go from one vertex to another, right? If these are two cities, now by using this edge, Alice can also go from 1 to 2, Bob can also go from 1 to 2, right? But by using this edge, only Alice can go from 1 to 2. Clearly, the preference of this edge is more than this edge, right? So this can be removed. We want to traverse the graph fully by using the minimum edges, right? And so this is, here we can see that this is clearly an extra edge available, right? So the preference of type 3 edge is always more than 1 and 2. Why? Because both this edge is solving the problem of both Alice as well as Bob, right? So what we will do, we will sort this array in descending order by using the first index, right? By using the first column, right? So let's sort this array. 3 2 3 will come here. Now rest of these two edges can be in any order, right? Either one will come first or two will come first, right? So here what is present? 1 1 2, right? So we will sort this array on the basis of the first column, right? Why? Because type 3 edge is having more preference than type 1 and 2 edges, right? The preference of 1 and 2 is same, right? So the first edge is 3 is of type 3 and 1 and 2. So this edge will help to go from 1 and 2 for to Alice also and to Bob also, right? So we have traversed 2 vertex, right? So here the count will come 1 plus 1. Here also the count will 1 plus 1, right? Why? Because we have traversed the 2 vertex, 1 and 2, right? Next edge is, we have traversed this edge. Now next edge is 3 2 3. Now this is of type 3 and this will solve the problem of both Alice and Bob, and this will help to traverse from 2 to 3. So it will help to traverse from 2 to 3. It will also 2 to 3, right? So edge will increase, vertex will increase by 1, right? So now by using these two edges, Alice can go from 1 and to 2 and Bob can also go from 1 to 2. Alice can go from 2 to 3 and Bob can also go from 2 to 3. So Alice and Bob are able to visit these three vertices, right? So next edge is 1 1 3. Now by using this edge, only Alice can go from 1 to 3, right? Why? Because this is of type 1 edge, right? So only Alice can go from 1 to 3. But we have already found a way. Alice has already found a way to go from 1 to 3. So we can ignore this edge, right? So we can ignore this edge and the number of remove edges is 1 because we can remove this, right? Next edge is 1 to 4. Now by using this edge, Alice can go from 2 to 4, right? So previously we haven't find any way by which Alice can visit the fourth vertex, right? So we need this edge, right? So Alice can go from 2 to 4, right? Now Alice find a way to visit all the vertices of this graph, that is all the cities, right? So we need this edge. Next is 1 1 2. Now by using this edge, the count is increased by 1 for Alice, right? Why? Because all the vertex 1 2 3 and 4 vertex are visited by Alice by using these three edges, right? Next is 1 1 2. Now by using this edge 1 2, Alice can go from 1 to 2, but Alice had already found a way to go from 1 to 2, so this is a, we can remove this edge, right? So the number of removed edges increases by 2, right? Next is 2 3 4. Now this is of type 2. This means that Bob can go from 3 to 4 by using this edge. So Bob had previously, Bob haven't any way to go to vertex 4, right? We have only go, Bob can only go to 1 2 or 3, right? So Bob need this edge to go to 4, right? So by using this edge, Bob can go to 3 to 4. So now Bob also find a way to visit all the vertex. The count of vertex increases by 1, right? Now we will find that if Alice is able to go to all the vertices of the graph, if Bob is able to go to all the vertices of graph, so count of A is what? 1 2 3 4. Count of B is what? 1 2 3 4. Now the total number of vertices in the graph is what? 4, right? So by using these 4 edges, Alice and Bob both are able to visit all the vertices of the graph, right? This means what, that the graph is fully traversable for Alice as well as Bob, right? So these two are the vertices that can be removed. Even after the removal of these edges, Alice and Bob are able to visit the all the vertices of this graph. So the maximum number of edges that can be removed from this graph is 2 only, right? It by using any other method, it can't exceed 2, because Alice and Bob require these 4 edges to visit the entire graph, right? So this is how we are going to solve this problem. We have to create a DSU for Alice and a DSU for Bob, right? So we will create a disjoint set union for Alice as well as Bob, and in the end we will check if Alice is able to visit all the vertices of the graph, if Bob is able to visit all the vertices of graph. If they are not able to visit all the vertices, then the answer is -1, that is we can't remove any vertex from this graph, right? Else we will return the number of maximum number of remove edges. This will represent that maximum this much number of edges can be removed from this graph, such that even after the removal of these edges, the graph is fully traversable for Alice as well as Bob, right? So this is the approach. So let's now move to the code part. So we will firstly create two DSU for Alice as well as Bob, right? So we will use the find as well as the union method of DSU, right? So firstly, let's we use the find method. We need the vertex and the ancestor of that vertex, right? So if we have the parent, then return that. Otherwise, find the parent of that vertex, the ancestor of that vertex, right? And mark that as the parent of that. Return the parent, right? This is the find function of the DSU, right? Next is the union function. We will use a parent array and a rank array, right? Let's make this function as a boolean type, so that it will tell us that if it is able to merge any of the two edges, right? So it will tell us that if it is able to merge the two edges, right? Firstly we will find the leader of X, right? Next we will find the leader of Y. Here we have to find y, right? Now we will check if leader of x is not equal to leader of y, then we have to do something and return true, right? Otherwise return false. Means that we can't merge these two edges, right? So here we will check if leader of x is less than leader of y, then parent of leader of x is equal to leader of y. Else if leader of x is greater than leader of y, parent of leader of y is leader of x, right? Next is otherwise, parent of leader of x is leader of y, increment the rank of leader of y by 1, right? So this is all about the union function of the DSU, right? So we will create the DSU of for both Alice as well as Bob, right? So next step is what? Here in the main function, main function that we are going to use, we have to create four arrays, right? Two for parent and two for rank, right? So let's create the parent of A, that is for Alice. This is of size n plus 1. Why? Because the numbering is start from 1, right? Because we are numbering the roots from 1 to 3 4, right? Next is parent of O. Next is rank of Alice, and next is rank of O. Is also of size n plus 1, right? But before this, what we were doing, we were sorting the array on the basis of the first column, right? So let's use the built-in function for sort, that is arrays dot sort edges a comma b. So it will sort the edges array on the basis of the 0th column, right? Next is what? Mark, initialize all these arrays, right? Initialize parent A, parent B, rank A, rank A and rank B. Initialize the rank array with 1 only, right? Right, so we are creating the DSU for both Alice and Bob. Next we will traverse on the edges array, right? So next we will check if the type of the edge, right? If the type is 3, if the type is 2 or 1, right? So next step is we are traversing on the edges array, and we will check the type of the edge, right? If the type is 3, this means that both Alice and Bob can traverse on the can use that edge, right? So we will check if we can merge the edges or not, right? So Let's name this variable as temp A. We will check if it is possible to merge the two edges or not, right? So pass the source and the destination and the parent array and the rank array. For A, pass it for B. Pass the parent and rank array for both, right? Next, we will check that if we can merge it for A, right? If we can merge, then merge these two edges. Also, we have to take the count also, right? We were taking these two variables, that is count A and count B, and also remove edges, right? So let's take these three variables, that is, let we name this as merged A. Initialize it with 1. I will tell you why, because move edge to 0, right? So we are initializing these two variables with 1. Why? Because when we are merging two edges, right? When we are merging two edges, then at the time when we merge this, then two of these vertex are going to merge, right? So we have initialized this with 1 only, okay? Right? Why? Because when we are using an edge, two of these vertex are going to merge together, right? So if it is able to merge the it for Alice, so increase the vertex count for Alice by 1, right? Next is if we can merge it for Bob, right? Then increase the merge count for Bob also, right? If we can't merge it for any of them, and that is if temp A and temp B is false, then increase the remove edge by 1, right? Right, that is it, they are these edges not useful for any of the vertex, right? When we are traversing this edge, then this edge is can be used by Alice to go from 1 to 3, but in the DSU there is already a path present for 1 and 3, right? That's why we are removing these edges, so we are incrementing the count of remove edge by 1, right? So if this is not present, for example for this edge can be used by both Alice and Bob to go from 2 to 3, right? So 2 and 3 is already not present in this DSU, right? So we are using this edge and we are incrementing the vertex count for both the Alice and Bob. Why? Because this edge can be used by both Alice and Bob, right? So this is the work for if the type of the edge is 3, right? Next, the same work is to be done for if the type of edge is 0, sorry 1. This means that this edge can be used by Alice only, right? So we will do this same work for only Alice, right? So we will do this work for Alice only. Else if it can't be merged in the DSU, this means that this edge can be removed, right? So increase the remove edge count by 1, right? The same work is done for bow else. So let's copy and paste it here, right? Next is after creating the DSU, we will check this count that if after removing the edges, if Bob and Alice both are able to traverse to all the vertices of the graph or not. So if merged A and merged B is equal to 1, right, is equal to the number of vertices present in the graph, then this means that we are able to find the maximum number of edges that can be removed, right? But if the count is not equal to the number of vertices present in the graph, then this means that the result for this will be -1. Why? Because it is given in the question that if we are not able to find the result, then we have to return -1, right? So if it is given that you return -1 if it's not possible for the graph to be fully traversed by Alice and Bob. This means that by using these edges, the graph is not traversed by Alice and Bob, right? So if it previously not traversed, then we can't remove the edges because it is not reversible by both of them, right, or either of them. So after doing this, we will check if the count, that is merged A or merged B, is not equal to the number of vertices. If merged A is not equal to n, or if either of them is not able to visit any of the vertex of the graph, then return -1, right? Else return remove edges, right? So this is the code, right? So let's try to run this. The name of, I think there is a mistake of the braces. Let's check this. This if is terminating here, else it will come, right? Either the type of the edge is 3 or 1 or 2, right? Also we haven't specified here the return type of the function. The return type of find function is int, right? So now let's check again. Here by mistake I have written bool. The return type of this function is boolean, right? Next is in the compare function. Here I think small c will come, right? Let's check whether the rest of the code is fine or not. We are taking 4 arrays, we are initializing them, we are traversing on the edges. Oh. Here we are passing the first the value of the in the first column and the value in the second column, right? So by mistake I have written 1 here also, right? Here also we are passing the edge, right? So to check if it is already present or not in the DSU, right? So now let's try to run it. So we are getting the correct answer, right? So let's try to submit it. So our code is getting submitted, right? So it is passing all the test cases, right? So what we are doing, that we are creating the DSU for Alice as well as Bob, right? Next we are checking that if it is already present, the vertex are already present in the DSU or not. So we are traversing on the edges array and also we are sorting them. Why? Because the preference of 3 is more than the any other type of edge, right? Why? Because 3 can be used by both Alice as well as Bob, right? So we are sorting this array. Next we are traversing this edges array and we are checking that if the vertex are already present in the DSU or not. If they are already present, then that means that this edge can be removed, right? So we are creating the DSU and using the find and union function of DSU. and we are using two variables merged a and merged b to check that if the graph is fully traversable by Alice or Bob, right? If it is not traversable, then return -1. Also take a remove edge variable to check to keep a count of the number of edges that we can remove, such that even after the removal of that much number of edges, Bob and Alice are able to traverse the graph fully, right? So this is the question. I hope the question is clear to you. So if you like the content, then give a like to this video. Thank you for watching.